Welcome to Lecture 4 of Civil Engineering Systems, dealing with project scheduling, otherwise known as things my project manager should have learned so I didn't have to end up on a middle of a dam in the middle of nowhere, Tennessee, where it has rained every day. The process of project scheduling is quite intuitive. It is a matter of first arranging activities into a diagram, table, or chart showing the start and stop times of various tasks involved with a project. It is important to keep in mind that as you do this, all activities must belong to a single project. It is also important to understand that each task is subject to precedence constraints. So, what do I mean by that? Let's take a project, like, say, a geotechnical investigation of a dam in Tennessee. We know that the very first thing that needs to happen is a utility survey, so that when we drill into the dam to receive concrete and soil samples, that we don't hit any power lines, water pipes, and things of that nature. We determined that the duration of this task should take 4 days to complete. Since this is the first task, it has no precedence constraints. It begins when the project begins. The next activity is concrete sampling. This task is projected to take 30 days to complete. However, it cannot be started until the utility survey is completed. That is the task's precedence constraint. The soil sampling is a task that is projected to take 40 days to complete. The start time for this task is also dependent on the completion of the utility survey. Now, since the soil sampling and concrete sampling are not dependent on each other, it appears that they can be done at the same time. Now, after we take concrete core samples, the next step is to send them off to get tested. This process is projected to take 15 days. Once the soil samples are gathered, we can send them off for testing. This should take 10 days to complete. Again, since there is no dependency between the concrete lab testing or the soil lab testing, these two tasks we can assume can be done at the same time. Finally, after all of the data has been collected from the sampling and testing, we can write the geotechnical report for the client. This should take us 3 days to complete. So, one way we can illustrate this project is to gather all of the projected durations and start times of each task and put them into a Gantt chart like you see here. We have the tasks on the y-axis and the number of days on the x-axis. We can see that the start times for the two sampling tests is 4 days since the beginning of the project, because they are dependent on the utility survey. We can also draw these lines on the chart to help us show which tasks are dependent on which preceding task. You can see how the concrete testing must come after the concrete sampling, and that the soil testing must come after the soil sampling. But the geotechnical report cannot be started until both of these tasks are complete. So the Gantt chart is great to help visualize the time span of the overall project as well as individual tasks. But as a project becomes more complex with more and more tasks, it is important to see the durations and precedent constraints and how they affect the outcome of the overall timeline and subsequent tasks. This is where the arrow diagram becomes helpful. An arrow diagram simply looks at a project as a combination of two things: events, which are shown as numbered circles or nodes, and activities, which are shown as arrows. Events can represent the beginning or end of one or more tasks. As we assign each task a duration, we can then use this diagram to figure out how this affects the start and finish times of all the forthcoming tasks. As we create the arrow diagram, we can label these start and finish times directly on the illustration. In this example, we have events 3 and 4. Event 3 represents the beginning of task 3-4, while event 4 represents the completion of task 3-4. The earliest start time, or EST, of either of these events is represented as an arrow pointing in the direction of forward time. When we place this arrow directly over the corresponding event or node. The latest start time, or LST, of a task, in this case task 3-4, is shown below and towards the start of the arrow. The earliest finish time of a task, task 3-4, or EFT, is shown below and towards the end of the arrow. And finally, the latest finish time, or LFT, of events 3 or 4 are shown as arrows pointing in the direction of time backwards above the node. We also show the duration, or D, of the task located in the middle of the arrow. Once the arrow diagram is complete, we use this symbol of parallel lines to illustrate the critical path of the project schedule. And that's something we're going to get into a little bit later. So let's look at our geotechnical investigation example and build an arrow diagram. So the first thing we put down is a node representing event 1. This event is the beginning of the project. Event 1 also represents the beginning of the utility survey, or task 1-2. We show the 4 to represent the 4-day duration, and the node with the 2 to represent the completion of task 1-2. Now, since we concluded that the concrete sampling and soil sampling can be done at the same time, we draw 2 arrows out of event 2. Remember, event 2 represents the end of the utility survey task, which both of these sampling tasks are dependent upon. So we draw task 2-3 as the soil sampling with a 40-day duration, and task 2-4 as the concrete sampling with a 30-day duration. Now, since the soil lab testing is only dependent on the soil sampling, and the concrete testing is only dependent on the concrete sampling, we can draw them dependent from those tasks alone, and happening at the same time. Now, we know that the next task is dependent on the conclusion of both of these tasks, so they can point to the same event, event 5. So, task 3-5 represents the soil testing with a 10-day duration, and task 4-5 is the concrete testing with a 15-day duration. Finally, the geotechnical report, which is dependent on all of the testing data being concluded, is shown as task 5-6 with a 3-day duration and ending at event 6, representing the conclusion of task 5-6 and the conclusion of the project as a whole. Now, in order to determine the project end date, we use what is called the forward pass. We start with node 1 or event 1, and we give it an earliest start time of 0 days. We then simply add the duration of the task to the earliest start time of 0 to get the earliest finish time of task 1-2. So, as you see in this equation, the earliest start time of event 1 plus the duration of task 1-2 is equal to the earliest finish time of task 1-2. This value for the earliest finish time of the task then becomes the earliest start time of the subsequent event, as shown in this equation. Now, this is important. If an event has multiple tasks pointing to it, the task with the greater or latest earliest finish time becomes the earliest start time of that subsequent event. Which makes sense, because if you have two tasks that need to be completed before taking on another task, the task that takes longer will determine the start time of the following task. So let's use our geotechnical investigation example. Here we show the earliest start time of event 1 as 0. We then simply add the duration to the start time to get an earliest finish time of task 1-2 of 4 days. This value, the earliest finish time, then becomes the earliest start time of event 2, meaning that the earliest that we can begin sampling concrete or sampling soil is in 4 days after the project begins. We then add the duration of each of the tasks to the earliest start time, which gives us an earliest finish time of 44 days for the soil sampling, or task 2-3, after the project begins. We also get an earliest finish time of 34 days after the start of the project for the concrete sampling, or task 2, 4. These values then become the earliest start time for the respective subsequent events. Again, we add the durations to the earliest start times and get earliest finish times of 54 days for task 3.5 and 49 days for tasks 4.5. Now, since we have two tasks flowing into event 5, the task with the greatest earliest finish time controls. So, the earliest start time for event 5 is 54 days. We then add this value to the 3 days it will take to rate the geotech report and get an earliest finish time of task 5.6 of 57 days. So event 6 represents the end of the project. Therefore, the earliest start time of event 6 represents the earliest possible time we can complete the project by. And since task 5.6 is the last task, the earliest finish time of 57 days becomes the earliest start time of event 6. Therefore, the earliest possible date of this project is 57 days after the beginning. So if you look at the Gantt chart from before, we see that as we compiled it, we also got a completion date of 57 days. Now, in order to determine the latest times of each task, we need to use the backward pass. We start with the due date or earliest start time that we determine from the last event of the forward pass. This value then becomes the latest finish time of the last event. We then move backwards through time, subtracting the duration of each task to give us the latest start time of each task. As you can see in this equation, the latest finish time of the event minus the duration of the task, mn, is equal to the latest start time of task mn. The latest start time of the task then becomes the latest finish time of the preceding event, as shown in this equation here. Now, if multiple tasks flow backwards into a single node, the task with the least or earliest latest start time controls the event's finish time. So let's continue with the geotech investigation example. I grayed out the results from the forward pass so that we can still see them but not be distracted by them. So the earliest start time for the node 6 of 57 days becomes the latest finish time of event 6. We then subtract the 3 days of task 5.6 to get a latest start time of task 5.6 of 54 days, meaning the latest time we can start the geotech report writing is 54 days after the project begins. This value then becomes the latest finish time of event 5, 54 days. We subtract the 10 and 15 days from the 50 days to get latest start times of 44 days for task 3.5 and 39 days for task 4.5. These values then become the latest finish times of their preceding events. Again, we subtract the durations from the latest finish times so that we get a latest start time of task 2-3 of 4 days and a latest start time of task 2-4 of 9 days. Now, since we have two tasks flowing backwards into event 2, we choose the least or earliest latest start time to control. So we get a latest finish time of event 2 of 4 days. We then subtract the 4-day duration of task 1-2 and get an LST of 0 days, which then ultimately becomes the latest finish time of event 1. So the last step in completing the arrow diagram is determining the critical path. This is the flow of tasks where there is essentially no wiggle room between the earliest start time and latest finish time of events. So we follow along where the difference between the EST and the LFT is 0. So as you can see, the critical path is from events 1 to 2 to 3 to 5 to 6, meaning a delay in these tasks would affect the end date of the whole project. You notice that the concrete sampling and concrete lab testing can be delayed for a few days, and it would not affect the project due date. So, how many days can either of those tasks be delayed? Well, that brings us to our next topic. Float is a way to determine how much each activity can be moved in time without affecting subsequent tasks and the overall timetable of the project. There are 5 types of float. The first is total float, and this basically determines how long a task can be delayed without increasing the duration of the task. Free float is the maximum amount an activity or task can be delayed without delaying the earliest start time of any of the succeeding activities. Interfering float is simply the difference between the total float and the free float. Independent float is the additional activity to be delayed without delaying the earliest start time of the task's immediate successor. And finally, safety float is the additional amount of time an activity can be delayed without increasing total duration. So, next, let's look at the equations for each of these more in depth. So, for total float, there are 2 equations we can use to determine total float. The first is we can take the difference between the latest finish time of the event representing the end of the task and the earliest finish time of the task itself. Another way to determine total float is subtracting the latest start time of the task and the earliest start time of the event representing the beginning of the task. So let's take a look at our geotech investigation example. If we look at task 4-5, which is our concrete lab testing task, it has a latest start time of 39 days. And event 4 has an earliest start time of 34 days. So we have a total float for this task of 5 days, meaning this task can be delayed 5 days before it affects its duration. The free float is the difference between the earliest start time of the ending event and the earliest finish time of the task. So for the concrete lab testing task, the earliest start time of event 5, representing the start of the report writing, is 54 days. But the preceding task, 4-5, which is the concrete testing, has an earliest finish time of 49 days. So we have a free float of 5 days between the end of one task and the start of another. Interfering float is simply the difference between the total and free floats. In our example, they are both 5 days, and thus no difference between the free and total float. So the interfering float is 0 days. Now, the independent float is the difference between the earliest start time of the ending event and the latest finish time of the beginning, plus the duration of the task. So, in our example, event 5 has an earliest start time of 54 days. The latest finish time of event 4 is 39 days. We add the duration 15 to the 39 days, and we get 54 days. So when we subtract it from the earliest start time of 54 days for event 5, we get an independent float of 0 days. This means we have no additional activity that can be delayed without affecting the earliest start time of event 5. And lastly, we have our safety float, which is the difference between the latest start time of the task and the latest finish time of the beginning event. In our example, we'll look at task 2.4, the concrete sampling. The latest start time of the task is 9 days, while the latest finish time of event 2 is 4 days. So we have a safety float of 5 days. So let's try a more complex arrow diagram. All we really know about this arrow diagram is the flow of the tasks and events and the durations of each task. We start with an earliest start time of event 1 of 0 days. We then add the duration of all the tasks coming out of event 1, and we get earliest finish times of 7 for task 1-2, 6 days for task 1-3, and 9 days for task 1-4. These values then become the earliest start times for their subsequent event nodes. We then add the durations of the tasks to the earliest start times to get a earliest finish time of 12 days for task 2.5, 9 days for task 3.5, 15 days for task 4.5, and 17 days for task 4.6. Now, the earliest start time for event 6 is simply the earliest finish time of task 4.6, 17 days. But for event 5, we have 3 tasks flowing into it. So we have to select the greatest earliest finish time of the tasks flowing into it. In this case, we select 15 days to become the earliest start time of event 5. We continue on by adding the durations and getting earliest finish times of 20 days for task 5.8, 20 days for task 5.9, and 24 days for task 6.7. These values then become the earliest start times for their subsequent events. We then add the durations to the earliest start times to get earliest finish times of 28 days for task 8.10, 27 days for task 9.10, and 32 days for task 7.10. Thus, we select the project due date of 32 days from the start of the project. Now, let's begin the backwards path to determine the latest start times. The earliest start time of 32 days becomes the earliest finish time of event 10, 32 days. We subtract the durations from the 32 days to get a latest start time of task 8.10 of 24 days, latest start time of task 9.10 of 25 days, and the latest start time of task 7.10 of 24 days. These values then become the latest finish times of their preceding events. Again, we subtract the durations from the latest finish times to get latest start times of 19 days for task 5.8, 20 days for task 5.9, and 17 days for task 6.7. For event 6, the latest finish time is simply the latest start time of task 6.7. But for event 5, we have 2 events flowing backwards into it. So we need to select the least latest start time, which in this case is 19 days. And this becomes the latest finish time of event 5. We continue by subtracting the durations to get latest start times of 14 days, 16 days, 13 days, and 9 days for tasks 2.5, 3.5, 4.5, and 4.6 respectively. These values then become latest finish times for events 2, 3, and 4. We subtract durations one more time to get latest start times of task 1.2 of 7 days. Latest start time of task 1.3 is 10 days, and latest start time of task 1.4 is 0 days. We then select the least latest start time of 0 to represent the LFT of node 1. We then look at the differences between the earliest start times and latest finish times of each event to determine the critical path. And we find that the critical path is task 1.4, 4.6, 6.7, and 7.10. This is because the difference between the earliest start times and latest finish times of each of these events is 0. So as an offline assignment, I would like you to copy this table in Excel and fill in the blanks. We already determined the duration, earliest start time, earliest finish time, latest start time, and latest finish time, but please fill them in anyway, since it will help you to fill in the blanks for the total float, free float, interfering float, independent float, and safety float. When you see the E and F, these refer to the numbers in the task. So, in this cell, you will be putting the values for the total float of task 4.5. Please complete this and email it to me before October 16th. So to recap your submittals, please complete the Pathfinder after problems for this chapter as scheduled. Also complete the Pathfinder before problems for the next chapter as scheduled. And complete the offline assignment I just gave you in the previous slide by October 16th in the form of a PDF emailed to me. Please email me if you have any questions with regard to this lecture or any homework assignments. Thank you and have a nice week.